Since the channel recently reached 163 subscribers, I thought I'd talk about some of the special properties that 163 has. So it may seem odd that this number even is special, but it turns out that it comes up a lot in number theory. So it has some interesting properties. Gauss actually came upon the number 163 when he was studying quadratic forms. So, well, binary quadratic forms, like x squared plus 3xy plus 20y squared and things like that with integer coefficients. And he came across 163 as a rather special number. In modern terms, it has to do with something called the class number. So in general, what you can do is take a field, so something like q root, well, a quadratic field, but you could do this for higher fields, but we'll just look at quadratic fields. So something like q root minus 7, and you look at the algebraic integers in that field. So that's the set of numbers that are roots of monic polynomials with integer coefficients. So the integers, well, the algebraic integers is, it forms a set z adjoin 1 plus root minus 7 over 2. So what that means is it's all numbers of the form a plus b times this thing here, where a and b are integers. Okay, and it turns out that this forms a ring. So if you multiply two numbers of this form, you get another number of that form, and it's pretty clear that if you add two numbers of that form, you get another number of that form. And the class number tells you basically how close this ring is to having unique factorization. So class number 1 means that it has unique factorization. So class number 1, well, that's equivalent to saying you have unique factorization. And then class number 2 means, well, you don't have unique factorization, but it's close in some sense. It has something to do with factoring ideals and things like that, but we won't get into that. So the special thing about 163 is that it's the, well, minus 163 is basically the last quadratic field, imaginary quadratic field with class number 1. So the last one where it has unique factorization. So q root minus 163 has class number 1. So that means that if you look at the integers in it, the algebraic integers, you take 1 plus root minus 163 over 2, and I join that to z. This is a unique factorization domain. Okay, so that's interesting in and of itself, but it turns out that if you go beyond that, like root minus 1,000 or 1,000,000 or even farther, there are no more with class number 1. And Gauss conjectured this, well, in the language of quadratic forms, but it wasn't proved until the, well, 1950s and 60s. It was originally proved by Hegner, but at the time, people didn't really acknowledge it as being correct. And then later it was, kind of patched up a bit by Baker and Stark in the 60s. So Hegner came along in the 50s. He was actually kind of not a very prominent mathematician. I believe he was a math teacher, He just happened to make this huge advance kind of out of nowhere. And unfortunately, it wasn't recognized as an essentially correct proof until after he died. Okay, so that's a bit of the backstory. And I wanted to talk a bit more about the consequences of this thing being a UFD. So that's interesting in its own right, but it turns out to have a lot of interesting consequences. Okay, these four things are all consequences of this unique factorization, but it may not be clear where on earth some of these things come from, but we'll see. I won't go through the proofs of everything, but I'll at least give some indication as to what's going on. Okay, so the first consequence is that if I take an odd prime p, then p is of the form x squared minus xy plus 41y squared if and only if minus 163 is a quadratic residue mod p. Okay, statement number 2 is that minus 163 is a quadratic non-residue for all odd primes p less than 41. When p equals 41, minus 163 is, I could add 164 to that, and I get 1, so that is a quadratic residue. But for any prime less than that, it's a non-residue. This next consequence was actually discovered by Euler long before all this class number business came about. But if you look at the polynomial x squared minus x plus 41, this is prime for all integers x between 1 and 40. So it's a huge string of prime numbers given by this quadratic. And last, and perhaps most mysteriously, is that if you take e to the pi root 163, this is almost an integer. Okay, so let's go through these one by one. First of all, we want to show that if p is an odd prime, then p is of this form. So for x and y integers, it's p equals x squared minus xy plus 41y squared, if and only if minus 163 is a quadratic residue mod p. Oh, and by the way, using quadratic reciprocity, this is the same as p being a quadratic residue mod 163. Okay, so let's prove these. First of all, I can assume that p is of this form. And then I want to prove that minus 163 is a quadratic residue mod p. So what I can do is basically just reduce this mod p. So I get x squared minus xy plus 41y squared is 0 mod p. And if I use the quadratic formula, okay, I'm being a little sloppy with my notation, I get y, x is y plus or minus root y squared minus 164 y squared all over 2 mod p. Okay, so x over y is, or xy inverse if you prefer, is congruent to 1 plus or minus root minus 163 over 2 mod p. Okay, and this thing has to be a square for this to be well defined. Okay, and so minus 163 has to be a quadratic residue for this square root to make sense. So that proves one direction. And in the other, we're going to use unique factorization. So we assume that minus 163 is a quadratic residue, and then we use unique factorization to get p in this form, as a quadratic form. Okay, so now maybe I'll separate this. So assume minus 163 over p is 1. So 163 is the quadratic residue mod p. So then, well, what I can do is there's going to be some integer so that t squared, some integer t, so that t squared plus 163 is 0 mod p. Okay, so basically p divides t squared plus 163 for this integer t, and I can factor this in my ring as t plus root minus 163 times t minus root minus 163. Okay, so now using unique factorization, if we think about the factorization of this thing into a product of primes, if p were irreducible, then it would have to appear in the prime factorization of one of those two numbers. So if p is irreducible in this ring, then p divides well, t plus minus root minus 163 or t minus root minus 163. Okay, but that can't be because then p would have to divide the real and imaginary parts separately, and well, that doesn't work because the coefficient here is 1 and the coefficient here is minus 1. Okay, so p is reducible. So that means that p is a product of two things, say alpha beta, and now actually this beta has to be the conjugate of alpha. So I'll write alpha times alpha bar. And now this is how we get our quadratic form. We want something like this. And now I write alpha as x minus y times 1 plus root minus 163 over 2. And then alpha bar is x minus y times 1 minus root minus 163 over 2. Okay, and then what happens when I multiply this out? I get exactly x squared minus xy plus 41y squared for some integers x and y. Okay, so that concludes the proof. So using unique factorization, we saw that if minus 163 is a quadratic residue, mod p, then p is represented by this quadratic form. Okay, so that proves the first part of what we wanted to prove. So I'll put a check mark next to that. Okay, now we want to show that minus 163 is a quadratic non-residue mod p for any odd prime up to, well, less than 41. Okay, that's actually a consequence of the first result, because if you look at the values that this quadratic form can take, you could write it as x minus y over 2 squared plus 163 over 4 y squared. And if we want to get a prime out of that, y can't be 0 because then we get p equals x squared. So this is at least 163 over 4. Okay, so if minus 163 is a quadratic residue mod p, then p is, well, this is just less than 41. So p is at least 41. So if p is less than 41, minus 163 is a non-residue. So that proves the second part. And now perhaps one of the first really interesting results is number 3. So Euler actually discovered this back in the 1700s before Gauss even considered these quadratic forms, and a couple hundred years before Heegner, Baker, and Stark came along. So we want to prove that x squared minus x plus 1 is prime for any integer x from 1 to 40. So now let's prove this result about the polynomial x squared minus x plus 41. So not surprisingly, we're going to do a proof by contradiction. So if x squared minus x plus 41 is composite for some x between 1 and 40, then what? Well, since x is at most 40, the biggest this quadratic can be is what we get when we plug in 40. And well, 40 squared plus 1 is 1601. Okay, so that means that if it's composite, at least one of the prime factors has to be less than the square root of this. So it has a prime factor p less than 41. Okay, but we're already in trouble because this thing has discriminant minus 163. So minus 163 is the quadratic residue mod p, but we just showed in part 2 that that's impossible. So this contradicts. So it's a contradiction mod p from result 2. Okay, so it's fairly straightforward from the unique factorization to see that x squared minus x plus 1 is prime for these 40 values. And actually this is, well, pretty much the best prime generating quadratic you can get. I don't think there is one that could possibly have more consecutive prime values because any quadratic that gives you a lot of consecutive primes essentially has to come from one of these fields with class number 1. And this is the biggest one, so this is the best you're going to do. When x is 41, well, each term is divisible by 41, so it breaks down there. There's a nice visualization of this result from Euler that this quadratic has a lot of consecutive prime values, which is to look at something called the Ulam spiral. So usually you start with 1 in the middle, and then, so maybe something like you start with 1, and then 2, 3, and you spiral outwards. Okay, so, and then you look at the primes, so 2, 3, 5, 7, 11, 13, and so on. And when you do that, there are actually quite a lot of patterns, which may seem odd. It isn't really a random set. You could compare it to a set of random numbers, and it won't look anything like that. And part of this has to do with these quadratic polynomials. So just to make it clearer, I've done essentially an Ulam spiral, but now I'm starting at 41 in the middle instead of 1. So 41's right here. And then I'm spiraling outward, 42, 43, 44, 45, and so on. And so these green numbers are the primes. So I've gone out to about 1700. And the yellow numbers are the numbers given by the quadratic polynomial, x squared minus x plus 41. So first I have 1 squared minus 1 plus 41, which is 41. And then 2 squared minus 2 plus 41, that's 43. So I've got 41, then 43. And then when I plug in x equals 3, I get this number, x equals 4, x equals 5. So I go back and forth. And the reason that this quadratic behavior becomes linear is that as I go outward, the numbers grow quadratically because, well, they grow in a way related to the area of this square. So it's quadratic rather than linear. So I end up with 40 yellow numbers on a diagonal. And if you look at the actual Ulam spiral, you see a similar thing, although it won't be quite this nice, where there are several lines coming from these prime generating polynomials. Okay, now the last and perhaps the weirdest consequence of all this is that e to the pi root 163 is almost an integer. So let me write out what it actually is just to convince you that this is something really bizarre. So e to the pi root 163, I'll write out the first several digits. So it's a big number, 262, 537, 412, 6407, 68743.9. And then I guess I'll keep going on the next line, 999, 999, 999, 99, and then 25, and so on. Okay, so it's extremely close to an integer. And, well, far closer than one would expect just from chance. I mean, we do have some irrational numbers here, but most of these, if you take some combination of e, pi, and a square root, you won't get something nearly this close to an integer. And something else weird is happening, which I'll mention in just a moment. So it turns out that this is related to something called the J function. And this is really too advanced to go very in depth. But the idea is you have this wacky function. The input is usually denoted tau, and the imaginary part of tau is positive for this to converge. But what you do is you write e to the minus 2 pi I tau plus 744 plus 196,884 e to the 2 pi I tau. And then the next term is 2149 3760 e to the 4 pi I tau, and so on. And of course, it isn't at all clear what this pattern is, but often the shorthand is to replace e to the 2 pi I tau with q. So since the imaginary part of tau is positive, this exponential has absolute value less than 1. So you get a power series that converges for q having absolute value at most 1 or less than 1. So j of tau is 1 over q plus 744 plus 196,884q, and so on. Okay, so there are these mysterious numbers. They end up being related to some very abstract group theory problems, the classification of finite simple groups and things like that. But now, one weird thing is this 744, because if you notice here, the last 3 digits before the decimal point are 743. So this is extremely close to a number ending in 744. That isn't a coincidence, actually, because there's a result that says that if I take tau, remember tau has to have positive imaginary part, if we take it to be 1 plus root minus d, so I'll explain what d is in a moment. So where I want this z adjoin 1 plus root minus d over 2, so the ring of algebraic integers, to be a UFD. Okay, so now the bizarre thing is that if this is true, then j of this value of tau is an integer. So j of 1 plus root minus d over 2 is actually an integer. Okay, so let's see what happens when we take d to be minus 163. So j of 1 plus root minus 163 over 2, well, what will q be? Q will be e to the 2 pi I times this thing, Okay, so this e to the 2 pi I over 2, that just gives me a minus sign. So I get minus e to the pi I times root 163. So that's e to the minus pi root 163. Okay, so let's see what happens when I plug this into J. Remember, the first term was 1 over q, so I get minus e to the pi root 163, which is a huge number, plus 744. And then I had some things with higher powers of q, but q is absolutely tiny. So informally, I'm just going to write plus tiny number. Okay, so and remember, this thing here is an integer because I have unique factorization. Okay, so what does that tell me? Well, if I move things over, I get e to the pi root 163 equals minus j of tau plus 744 plus this tiny number. Okay, so that's how I get this result that e to the pi root 163 is extremely close to an integer, and in fact it's an integer ending in 744.